Hello, this is David Bishai recording a lecture on economic models and systems. The outline for our lecture is to cover really two things in the next 15 minutes. We're going to cover a review of microeconomic functions, the production function, profit function, input demand function, and cost function. After illustrating these four microeconomic functions, we're going to connect them to our understanding of health systems. We're going to look at our agents, units, and institutions and see which of them are engaging in health production and which of them are expressing health input demand. This is the foundation for everything we need to do in the rest of the course. Our question is, how is health produced in a health system? And so that's the motivation for going back to the microeconomics of the firms and how things are produced in an economy. So section 1 is to go over those functions, and I've illustrated this with a donut production function, and you can see a vat of oil and some of the donuts emerging from the oil. There's capital and labor, giving us a sense of how one makes donuts. So if we go back to our functions used in microtheory, well, we want to cover four different functions, and this table displays the name of the function and what it takes in and what it puts out. So a production function named F, and F is its name, just like Harry or Susan or Karl Marx. It's a name, and it takes in inputs, and in this case it really takes in inputs. These inputs labeled by X are labor and capital and raw materials, and the output of a production function is Y. You'll notice that I used lowercase y for a scalar, a simple number of the number of donuts, but I put in uppercase X because it's a vector of many, many different inputs, labor and capital, etc. So that's our production function. We're going to review that in a little more detail in just a minute. The profit function, symbolized by pi, has a domain of input prices, output prices, the number of inputs and the number of outputs. That's the things that you put into the function. And out of the function comes a number depicting the profit that the firm has made that year. Third is the input demand function, symbolized by F inverse. The domain for this function is the optimal output, little y, and the range is the optimal inputs. You tell this input demand function how many donuts you want to make, and it will tell you how much capital, how much labor, how much oil, and how much flour to buy. Finally, for today, the cost function, labeled by C, has as a domain the optimal inputs, X star. You tell the cost function this is how much flour, sugar, and oil, and the cost function will tell you what it's going to cost to run your donut shop. So that's a foreshadowing of what we're going to cover today, and let's just go through some of the details first on the production function. So when we have a production function, we are generally in the business of transforming one thing into another kind of thing. So here's a picture of us on a farm transforming land and sky and clouds and sunshine. We take some fertilizer, we take some labor, we try to use our family labor if that's what's going on in our local economy, and of course there's going to be some rainfall. And these things that don't look like corn turn into corn, and a production process is a transformation process. If we want to use mathematics for this, we can symbolize the production process as little y equals f of vector x. An example of this would be the production of corn as a function of land and fertilizer, and just for simplicity I'm leaving out all the other things you can think of. So specifically, we are going to perhaps put on some mathematical formulation and say corn equals 0.3 times land to the 0.5 and fertilizer to the 0.5. This means we've really understood our farm production, we've studied it for years and years, and we know for sure that that's exactly how much corn you're going to get if you put in those amounts of land and fertilizer. If we want to draw that function, it would perhaps look like a parabola on its side. And on the vertical axis we have corn, on the horizontal axis we have fertilizer, and this would be a mathematical graph of our production function. So for an economist, farming is quite simple. I know for farmers it's quite challenging, but an economic model of farming really has the farmer as an economic agent with two questions. Farmer has to decide first, how much corn should I grow this year, which we symbolize by optimal Y star, and we're going to put asterisks next to things that are optimal. There is one best amount of corn for every farmer to grow this year to maximize profit, symbolized by Y star. And after you've answered how much corn to grow, the question is, how many inputs should I buy to make that much corn? And we symbolize that by vector X star. Now, the way the farmer answers this question is to obey the rule that revenue must be greater than or equal to costs. Because if not, then the farmer is bankrupt, the bank takes over and forecloses the farm. So revenue must be greater than or equal to costs. And for that to be true, the optimal Y star times the price of corn has to be greater than or equal to the cost of all of the inputs, symbolized by C of X star. Now I can take this revenue greater than or equal to cost inequality and turn it into a profit function, and I'm going to do that right now. Here you see that profit equals revenue minus costs, and I can symbolize profit by Y star times PY minus the cost of all of the inputs. One of the things we believe as economists is that in a competitive market, the agents all try to maximize profit. And in a perfectly competitive market, these agents are small and they cannot change prices. They can only choose how much output and how much input in their firm. So they solve their profit maximization problem for what is the optimal Y and what is the optimal X to maximize profit. And then when they have completed that maximization problem, we'll put an asterisk on little y and capital X. If we want to talk about how they do this, we say optimal Y star is the argmax of profit function. An argmax is the argument that you put into a function that maximizes it. So in this graph, I've drawn a profit function, which is a parabola today. And the argmax of this profit function happens right there at Y star equals, 50. If we put in the optimal output of 50, if we decide to produce 50 tons of corn this year, in this situation, we will have achieved the maximal profit. So that's how we use the word Y star in this context of a profit function. So if you're a producer and you have an F function, what do? Well, for example, let's suppose that Farmer Joe has gotten wind from the U.S. Department of Agriculture that his optimal Y star is 3 tons of corn. He didn't have to do this profit maximization problem himself. He got help from the government, maybe from an economist. And so now that he knows that his optimal output, Y star, is 3, he's going to want to make 3 tons of corn by September. And the question for Joe is, how much fertilizer should he order in May? And that he has 1 acre of land. So he takes his F function, his production function, corn equals 0.3 times land to the 0.5 times fertilizer to the 0.5. And he plugs in his values. He needs to make 3 bushels of corn, 0.3 times 1 acre of land to the 0.5 times fertilizer to the 0.5. So he is going to solve for what value of F will give him his 3 tons of corn. And if you do this, 3 divided by 0.3 is 10. 10 equals F to the 0.5. So that must be 100 pounds of fertilizer required for his farm. So what he just did was use an input demand function. He calculated the optimal amount of input needed to make the optimal output. He basically invented the inverse F function, which is an input demand function. And now he knows that X star equals F inverse of Y star. So for Joe, that function can forevermore be listed at the bottom of the slide as fertilizer equals corn divided by the 0.3 raised to the second power. Finally, let's talk about the cost function. If Joe knows the prices of all the inputs, then he can quickly determine how much it will cost him to make the profit maximizing amount of corn this year. Let's disclose the prices in this economy. Let's say that rent is $1,000 an acre. Let's say that fertilizer is $200 per ton. And so we can quickly calculate how much it will cost Joe for his farm production. It'll be $1,000 for his 1 acre, and 3 times 200 is $600 for fertilizer, and so it'll cost $1,600 to make the 3 tons of corn. So the way cost functions work is if you know the production function and you know the prices of all of the inputs, then you can make a cost function if you know the optimal amount of the inputs, vector x star. The cost function only works with vector x star, the optimal x. If you don't use the optimal x and you use incorrect amounts of your inputs, let's say you use 1 teaspoon of fertilizer on 100 acres, your cost function is not useful to anybody. It tells you a very wasteful way of making corn, and nobody wants to listen to it, and you're wasting your time talking about it. Only study costs of farmers and production agents that are optimizing and using the profit maximizing inputs into their production process. So, as it says, cost functions are only useful if someone is actually maximizing profit and minimizing costs. If Joe is wasteful, why do we care what his farm costs? We want to study the efficient producers in the economy. There are thousands and thousands of ways to be wasteful, and our cost functions won't be helpful. Now you can think ahead to a health economy when we have many agents that are not maximizing as they should. They might be working for a nonprofit company, for the government. They might be addicted to drugs, or they might like to eat donuts too much, and they might not be the most efficient producers to study. So let's re-examine the cost functions and profit functions. If we look at the profit function, pi equals y star times the prices minus the cost of the inputs, we know that y star is produced with its production function, and the cost function is calculated as x star times prices. So if I do substitution and I plug in the production function for y right there, I'm plugging in f of x star, and I'll get f of x star times py. And if I plug in for the cost function x star times p of x, now if you look at the profit function, I don't have y star in it anymore. Now the profit function can be determined completely by the prices of inputs, the prices of outputs, and the amount of optimal inputs. So the profit function can be a little bit simpler, and cost functions and profit functions are called dual to each other. They are always related to each other. If I know a firm's profit function, I can quickly determine its cost function. Likewise, if I know a firm's cost function, I can determine the profit function. So that's our quick review of micro theory and our functions from our prior study of microeconomics. Quiz time. I'd like you to look at the graph on this slide. There's a profit function, which is graphing profit on the vertical axis, and it goes from -10 to +15. And an input called fertilizer is on the horizontal axis, going from 0 to 1.2 tons of fertilizer. The question for you on the quiz is, what value of fertilizer is the argmax? So take a second and look at the graph and look at the choices. Choice A, it's 1 ton of fertilizer. Choice B, it's $12. Choice C, it's 0.58 tons. Choice D, cannot tell. So of course, the right answer is the argmax is the amount of fertilizer that goes on the horizontal axis, leading to the maximum amount of profit, which would be right around here at about 0.58 tons. So the correct answer is C, 0.58 tons. Now let's go on and study how we apply these functions in health systems. If we think about the health system, we think about what produces health. And in our view of systems, we know that there are units that transform sick people into healthy people. That's called the healthcare system. And if you're a hospital or a network of hospitals, if you're that whole big complex of health services, health supplies, quality, governance, the WHO's 6 building blocks, then you take as inputs pills and health worker time and surgeries and sick people, and you'll transform that into healthy people. But there are other producers of health. You're one, and you and your household and the people who live with you are a firm that produces health. So the household and the individual agent linked in that household are health producers. Neighborhoods, when they gather together to decide to make themselves healthy, are producers of health. Governments, when they decide to try to make their population healthy, are producers of health. They are units that have gathered together for the purpose of making health. Now, be careful, because sometimes governments in the past and in the present have said, no, we don't do anything to try to make the citizens healthy. If they die or live, it's their business. We are not even going to lift a finger to clean the air or the water or stop epidemics in their community. We do other things, but not health. And then if that's the stated objective, and that's what you can observe in their behavior, then you would say to that government, it's not a health producer. But for the purposes of the next few weeks of this course, we're going to study those governments that have actually decided to become health producers. So we're getting to the idea that every human being is a producer of their own health. And because of this, every human being must have an input-demand function for the inputs to health. They're going to have an F function as well as a input-demand function, F inverse. If they know how healthy they want to be, they will know how many donuts to eat and how many doctor visits to schedule for the year. So, question. Is there maximization? Are biological agents really trying to maximize their health? Well, Charles Darwin's answer was quite simple. He says, in the long scale of time, over hundreds of thousands of years, all of the biological agents that did not try to maximize their health are gone. They're extinct. They were competed out of their niche by their members of their same species that were trying to maximize, and only the maximizers passed on their genes over the 100,000 or million year scale of life. But how about humans? We've only been around for a few 10,000s of years. Are we really trying to maximize our health? Is Darwinian competition really happening? It's a good question, because we know there are several exceptions to biological agents with human species maximizing their health. We observe drug addiction and sedentary lifestyles and many choices of governments to do nothing to prevent epidemics. So we have to be open-minded about whether indeed we are seeing maximization, which is kind of exciting for economists. We have all of this machinery ready for the study of maximizing agents. Are we really maximizing? So for the rest of the course, we will be in health economics, where we are trying to study the health economy. We'll be studying trillions and trillions of dollars being spent on Earth to buy and sell health inputs. And we've started off our study by asking, are the buyers of these health inputs maximizing their health? Are the sellers of these health inputs maximizing profit? Remember, there are governments and nonprofits selling these health inputs, and we don't know if they maximize profit. We're going to study the cost and the efficiency in this system of selling and buying. And I'd like to start with the concern that the costs might not be so meaningful if the agents are not maximizing. We're studying health economics because we want to help the system do a better job, and we're looking at this through a systems lens because we want to think of institutions, rules, ways of playing the game that would help a health system do a better job at achieving its goals. And we need to discuss, and we will discuss in class, what are the goals of the agents in a health economy. So, let's wrap up. Each individual is a producer of their own health. The way our micro theory works is that now the individual is a firm producing their own health. And they often gather together in social groups. They form families and households that co-produce the health of the members of the household by deciding what to eat together, how to manage their epidemics and infections together, whether they cover their cough, whether they wear masks inside the house, etc. They do produce health as teams. And on a somewhat larger scale, whole communities and neighborhoods are units that produce health by the way they treat their neighborhood. Diseases can be determined by how fast we speed in our cars and whether we wear masks and walk around with social distancing. Because of the machinery of the theory of the firm, these agents and units will have a demand for inputs into the health production function. They will be interacting with each other in ways that can be coherent and symbiotic or not. When they engage in activities, all of those activities will have costs, and we can use a cost function. But if they are not maximizing their production process, their costs might not be that important. And until we've produced some sense of efficiency in their system, we'll have to keep an open mind about what those costs mean.